Welcome back. So can you, am I audible and can you see my screen?
Yes, sir.
Okay. Okay, so I made a small mistake here in the calculation, but it finally it didn't change anything in our analysis. So, so when we are here, so since we assume that these Zi tilde are IID, so we can write it this raised to power k, and we are writing this as raised to power k. The term this k will not be here, right? So this should not be here, right? And so basically this k should not be here. Similarly, this k should not be here. This k should not be here, and the rest of the things are fine. Right? So and here it should have equality. Okay, so yeah, so this is some small mistake I did. So this k should not be here.
Sir, there was a video lag. Can you repeat that again?
Okay, so earlier we had this term k over here, and which were like this term k, yeah. So here we had this term, and so since this zi tilde are IID, we basically raise this random variable raised to power k. But when we are raising it raised to power k, this term should not be here. It should go in the exponent, right? So this term and that term will keep on with us until the calculation. So this term should not be here. Like this term will just remove, right? And rest of the things are fine. Should be epsilon by 2, and rest of the things are fine. Okay. So what we have shown is that probability that this is our norm of compressed probability that the norm of compressed vector is more than 1 plus epsilon times norm of the original vector is at most 1 by n square. And similarly, we'll show it. So this is, maybe I'll just name this equation 1. Similarly, we show that probability one by root k or x whole square is smaller than 1 minus other side of the inequality will show is at most 1 by n square, right? So again, we start with this term. And again, we'll write it like this: sigma zi tilde square I from 1 to k is less than 1 minus epsilon times k, where as previous this zi tilde is rx j by norm of x, where this zi tilde are IID. Okay, the same way which we did in the previous, the first part. And again, we'll, for simplicity, we denote this z as sigma Z I tilde square I from 1 to k. Okay. Okay. So now what we can do, so can we apply Markov here? Right. So for Markov, this inequality is in opposite side. So we'll do some trick. Okay. So we'll just write for any lambda greater than 0, for any right. And now we'll just erase this in the power of exponent. E raised to power minus lambda z is greater than e raised to power minus 1 minus epsilon lambda k. Now we can apply Markov's here. Okay, everyone with me? So now if we apply Markov, what do we get? E raised to power.
Expectation of e to the power minus lambda z
Yes.
divided by e to the power minus 1 minus epsilon lambda k.
Lambda k, right. Very nice. Okay. And again, we'll do the same thing. We'll just e raised to power minus lambda sigma z I tilde square I from 1 to k by e raised to power minus 1 minus epsilon lambda k. Right. And again, we can just write this in terms of product I from 1 to k e raised to power minus lambda z I square. Okay, and since these z I tildes are IID, we can write this as expected value of e raised to power minus lambda square right? Okay, and again, we'll use the same fact. Yeah, yes, so we'll again use this fact. So it says that E of raised to power minus lambda zi square is most 1 minus plus 2 lambda. using the same fact. Only the sign of lambda is different. So we'll put it over here. So we'll get 1 plus 2 lambda square root 2 lambda and e raised to power minus lambda 1 minus epsilon raised to power k. And again we choose the value of choosing lambda is equal to epsilon upon 2 1 minus epsilon. So just for sake of simplifying the things, we get 2 e raised to power minus epsilon raised to power k over 2. And again, we'll just do the same type of calculation, e raised to power minus lambda plus log of 1 minus epsilon raised to power k over 2. And again, we do the same type of expansion. So we get e raised to power minus epsilon this is minus epsilon square by 2 epsilon cube by 3 so on to power k upon 2 and again choosing basically k of order log n upon epsilon square minus epsilon cube. I'm just hiding the constant for simplicity. So we get this term is basically we get e raised to power minus 2 log n upper bounded by minus 2 log n and which is 1 by n square. Right. So this is equation 2. So both equation this and the previous equation this shows that probability that 1 by root k rx norm of this it doesn't belong the interval of 1 minus epsilon x square and 1 plus epsilon of x square within 1 plus minus epsilon uh, interval of its original norm is at most 2 by n square. Right. So any doubt until this part? So we follow roughly the same calculation which we did in the first part. Yes or no? Just can let me know if there is any trouble in understanding any of the steps.
So one thing, yeah, proof is fine. So if you go back to the concentration definition, I mean that beginning where we started.
Yes. Okay.
Yeah. Just can you explain like why? Yeah. So just can you explain like why we get this greater than epsilon should be less than small delta. So that part, the 2 points, one and two.
One second. Here.
To the bounds of error, concentration bounds.
So this is the concentration bound, but we have not proved until this point. So
Yes,
which
yeah. So this is the definition of the Johnson
yes,
Linden
Linde's
stress. Yeah.
yes,
So
yes.
then we went for concentration where we, before starting our proof, we have 2 points, right? Probability of Rx square. If you go down a little bit.
Hmm. So we have
Yeah, not before the proof.
So when
yes.
you're
Yeah,
defining two, this one.
yeah, this one. So can you explain like how we came to this 2 point? Like,
So this is what we proved now. So this
yeah,
we
we
start.
have proved, but yeah,
Hmm.
we have proved, but why we, I mean, how we get that? I mean, what is the definition? Why we said this? I mean,
Okay,
basically, from the definition, how we came to this definition of concentration.
fine. Okay, so here, okay, okay. So here we are. So here there are two things. So here, so this definitions is for data set, right? So if we here we says that if we consider a data set which has say n point, so then the pairwise estimated distance remains within 1 plus minus epsilon of the original distance, right? So this is the original JL lemma thing, and we are proving it by construction. So what we are showing it, okay, so here we are, so this random matrix R is one such possible instance of F. So we are trying to show this inequality holds with high probability, right? So this is what we are
Okay.
trying to state here. So basically, if you see these two terms closely, so this, if we just can add one line here, like the following holds with high probability, then essentially this is nothing but these two statements, but for only one point, and we'll see how to extend it for pair of points. So this is for one point. So here we are saying that if we follow this kind of function f, then uh, the norm expected value of basically then the norm of our compressed vector, it's remains within 1 plus minus epsilon range of the norm of the original vector, right? And here we are stating it with high probability, and here we are stating it in terms of pairwise distance, right? So just to answer your point, your questions, we are proving the JL lemma by giving one instance of F, and we are showing that this guarantee holds with high probability, right? So does this answer your question?
Okay. Yeah. Yes, sir.
Okay. Okay. So far we have talked about one point in our data set. Okay. Hmm. So far we have talked about one point in our data set, but this easily extends to basically pair of points. So suppose if we have say so suppose this is our random matrix R, which is, and this is our D cross 2. So suppose we have say 2 points, say maybe x1 and x2. Okay. And this is 0, and this R is K cross T. So after applying these two, we'll get matrix of size k cross 2, right? And this is basically our x1 and this is our x2, right? Now suppose if we want to prove this thing, then what type of guarantee we need to show here? That probability 1 by root k are x1 minus x2 x1 minus x2, it doesn't belong to 1 minus epsilon x1 minus x2. Is 2 by n square. Okay, so this will be kind of analogous statement for pair of point, right? So does this make sense? So here what we are saying that, okay, if there are 2 points in our data set, then we calculate the distance in the compressed representation. So that remains within 1 plus minus epsilon factor of their original distance with probability at least 1 minus 2 upon n square, right? So does this make sense? So this you can think of estimated distance in pressed vector, and this is original distance, right? Yes or no? You can just interrupt me if you have any doubt on this point.
So the same holds if you have x1 and x2 and x3.
Yeah, so we'll come to that. So first, for now, for simplicity, just consider that there are 2 points. So are you convinced with this point? Like this, we can easily achieve with this. Basically, this equation 3, and this is suppose equation 4. So basically, we can get equation 4 easily from equation 3. So all we need to do is just to replace
X with x1 minus x2.
x with x1 minus x2, and the same proof will go through, right? And this is the estimated. So this part is the estimated distance, right? And this you can see that so our original compressed vector is rx1, and the first compressed vector is rx1, second compressed vector is rx2, and if we calculate, basically we can take out r common. So this is 1 by root k. And if we calculate the norm, it will be this, right? Basically, equation 4 holds via 3 just by putting x as x1 minus x2, right? So for 2 point, we are good. Now what happens if we have more than 2 points? Say if we have, say, n point, okay? So So I'm just denoting this event, say probability of Eij as probability 1 by root k r xi minus xj doesn't belong to 1 minus epsilon xi minus xj 1 plus epsilon xi minus xj. Okay, so this I'm just writing it for brevity, and this is at most 2 by n square. So this state that, okay, uh, the probability that xi estimated pairwise distance of xi and xj from their compressed representation doesn't belong to 1 plus minus epsilon range of their original pairwise distance is with probability 2 upon n square, right? Now, if we have, say, n such point in our data set x1, x2 to xn, then what we want? We want this to be happen for all the points, all pair of point. So we want to upper bound, we basically e of ij, where I comma j from n, right? And now what we can do here, we can apply union bound, right? So this is probability of Eij I comma j belongs to n, and this by union bound. Okay, and so basically this one term is 2 by n square, and there are n choose 2 terms. So we left with basically 1 minus 1 upon n. Right? Any doubt on this part? We didn't do anything fancy. We just applied union bound for all pair of points. Okay, yes or no? Like, let me know if you have any doubt on this.
So that n by 2 is because you are taking pairs of points, is it?
No, and choose two. And choose two pair.
Oh, sorry. Okay, okay, yeah, and choose 2. Okay, yeah.
So for one pair, the guarantee is 2 by basically you can think of this thing as a bad event. The estimated pairwise distance is out of the range we want. It's with probability 2 upon n square. So
So last one will be less than equal to, right? Just a
yes,
typo.
yeah, this one, yeah.
So is there any other method of dimensionality reduction apart from this
Yes, so we'll come to that. Okay, so so I hope you are comfortable with this. So it says that probability that for any pair, the basically the estimated distance followed with the desired distance is smaller than 1, but we can boost it using our standard boosting technique, like uh, repeating it log 1 over delta, order log 1 upon delta times, and to boost this to any delta greater than 0. Right? So this, I hope you can able to extend it. Okay, so in the analysis, all the things we have covered. The only thing which we have not covered is the fact that we used. Okay, so what we use, that we use something of this type. E raised to power t x square. So proving the fact. Okay, so this, where x is from normal distribution. Right, in our notation we used it z. So here, if x is basically, I'm writing it more generic. So essentially, it is computing MGF. So if x is normal distribution, then what is the distribution of x square? So if x is say normal, then x square is called chi-square distribution. And essentially, this is nothing but computing moment generating function, computing MGF of chi-square distribution. Okay. So this is what? This is e raised to power tx square into distribution, which is 1 by root 2 pi e raised to power minus x square by 2 dx. So essentially, we need to calculate this integration, and that's the only kind of technical part. E raised to power minus 1 minus 2t upon 2 x square dx. Okay, and this is somewhat kind of not so involved, but yeah, somewhat this thing. So it's basically here we do the change in parameter. So we go from this coordinate to polar coordinate and solve it. So essentially, after solving this, we get 1 minus 2t, right? By changing the variable. So this part is kind of fairly algebraic. So I'll not cover this in the class, but either you can believe it's true, or you can just try to solve it on your own by putting the value, changing this to polar coordinate, and then solving it. And finally, you will get this. And this is the only thing which we use in our analysis, right? Okay. So in our JL lemma, for JL lemma, if we just summarize, our input is real valued vectors in form of matrix, and output is again compressed, basically real valued vector or vectors in low dimension or compressed vectors. Okay, and what it in what similarity or distance measure it follows. It approximates pairwise Euclidean distance. Okay, similarly, the same kind of analysis we can also extend it for pairwise inner product. Okay, and what is our algorithm? Is essentially generate a random matrix and multiply with input matrix. Okay, so suppose our input matrix is of size D cross N, and we generate a random matrix of size K cross D, where K is order log n upon epsilon square. Then basically it's and third step, yeah, basically then generate a random matrix and multiply with the input matrix. And this is also called as random projection. Right. And the constraint is that we choose entries of the matrix R from normal distribution. Okay, so this is RJ1, RJ2, RJD. Suppose we have other entries of the random matrix R. And this was our input x1, xt. Then we get Rx. Such that this Rxj is what? This Rxj was sigma Rji xi I from 1 to d, right? And these Rij are from normal distribution. Okay, so this was our JL lemma, right? So now there are several follow-up results. So essentially, if we choose the entries of Rij from normal distribution, so this will be some, each entry will be some real valued number. So maybe 0.6, 0.7, 0.99, 2 point something like that. So this will be some real numbers, and then we need to multiply this with our input matrix. So the subsequent follow-up result shows that okay, we don't need to choose this entries of this random matrix are from normal distribution, we can choose these entries from a much more simplified distribution, such that this kind of matrix multiplication time could be somewhat faster, right? So can you suggest any other distribution using which, if we choose this Rij, we'll get an E of R x j square is norm of x square. So can you suggest any other distribution if we choose using which we choose this Rij, we'll get this guarantee? Okay, so just let me just write few more steps and then maybe. Okay, so this Rxj is what? Sigma Rji xi I from 1 to d square. Okay, and if we just expand this, what do we get? R ji square xi square I from 1 to d plus sigma I not equal to I prime R ji R j I prime xi into xi prime. Okay, and I'll just write one more step. Sigma I from 1 to d xi square expected value of R ji square plus sigma not equal to I prime xi prime expected value of R ji into expected value of ji prime. Okay, so now if we choose this rji from this normal distribution, this value is 1 and this value is r0, right? So finally, like this term get cancelled out, and here we get norm of x square. So can you suggest any other distribution using which we choose rij will get the same expectation? This sort of thing we have covered in the class. In last class, in fact. Anyone? So just notice that we want these property to be satisfied. So basically our distribution should be such that expected value of rji square is 1 and expected value of rji should be equal to 0. So how should we choose rji from which distribution? Any guess? So in count min sketch, what did we use? We used two hash functions. One hash function h that maps to several bins, and there is another hash function g. What was g?
It's range from -1 to +1.
Yes, so we can choose this Rij from set -1 or +1, each with probability half. Right? So if we choose Rij from +1 and -1, then your Rij square is Rij square is 1, and expected value of Rij is 0. Right? So this is what we want. So in fact, if we use this distribution, expected value is same, and we can. It's also possible to show the same concentration guarantee. Right? So essentially, like, we can replace this Rij from normal distribution to Rij from this +1 and -1 with probability half. Right? So each entry for each, basically to generate this random matrix R. So suppose if you want to determine the entry of this position, we'll just toss a coin, and based on the result, we can put it either +1 or -1. Right? So even in the same calculation, we can. It's easy to see that the expected value of the norm of the complex vector is the norm of the original vector. Of course, we need to do this 1/√k scaling. But what is the advantage of using this +1 and -1 over normal distribution? So if you use this normal distribution, basically we need to calculate this term. So this term will be what? Basically, we need to multiply each coordinate of x with some real numbers, right? From normal distribution. But here, if Rij is from +1 and -1, so essentially what we are doing. So it's basically we reduce the multiplication with just addition and subtraction, right? So is this point clear? So what I'm trying to say, if we choose Rij from +1 and -1, then this term is what? So this term will be what? Basically x1 plus x2 minus x3 minus x4 plus x5 and so on, depending on the term, like depending on the value of Rij. Suppose your R11 is +1, R12 is +1, R13 is -1, and so on. So this is basically we are just what we are doing. We are grouping the features of xi and performing addition and subtraction. But here, if Rij is from normal distribution, we need to multiply these features with some with some real numbers, right? So that is somewhat more computationally involved, right? And finally, we get, it's also possible to show that, in fact, it has been shown that this, if we choose Ri with this distribution also, we get the same concentration guarantee, right? So does this make sense? And this is, in fact, a very famous result, which is called database friendly random projection. Due to CHLI PTAS Ecliptus, and it appeared in PODS 2001. Okay, so this is basically, you can think of this as improvement over standard random projection. And there are subsequent results which say that, okay, and this is also called, this distribution is also called Rademacher distribution. Okay, so there is another subsequent result which is called as very sparse random projection, which says that basically we can make the entries of this projection matrix 0 at lots of the places, right? So we can choose this Rij with probability 1, with value, take value 1, 0 or -1. So 1 could be with probability 1 by 2s, 0 could be with probability 1 minus 1 by s, and this could be with probability 1 by 2s, right? And we just need to scale it by root of s. So essentially, if we choose S as 1, then it is boils down to this database friendly random projection. And again here, you can calculate that E of.
Could you please use the brighter ink? Looks like it. The color is very faint. Yeah.
Color is not fade, but I think I has, or maybe I'll use red for now. Yeah, so I think I zoomed it, and then if I zoomed it, then the color gets faded. Okay. So here again, we can show that expected value of Rij, expected value of Rij is what? For s greater than equal to 1. So expected value of Rij will be what? 0. You can also show that expected value of Rij square is 1. And again, if we put these things over here in this equation, we'll get the compressed expected value of norm of compressed vector is the norm of original vector. And also it's possible to show, like it has been shown, the same concentration bound. So here the advantage of using this Rij. So suppose if say we choose SSA 3, right? So this will be what? This is with probability 2 upon 3. And this is 1 by 6. And this is 1 by 6. So it's saying that roughly in 2/3 positions of the random matrix R, we are putting 0. And on the remaining 1 by 6 and 1 by 6 positions, we are putting -1 and +1. Right. So if there are lots of 0 in the projection matrix, then basically lots of 0 in this matrix R, then the matrix multiplication could be faster. Right. So suppose if you need to multiply this with some matrix, and if there are lots of 0 in this, then basically the matrix multiplication could be done faster. So this is the main advantage of using these distributions. Okay, and they also follows. I can show the same. Guarantee. Okay, and this was very sparse random projection due to this Lee, Este, and Church. It appeared in KDD. Okay. So any question until this point? Okay, so that's all I had for today. And